In this video, I'm going to be talking about the dot product and how we can multiply two vectors together by using its method. And I'd like to start off this video by just stating that there are actually several ways to multiply vectors together. And this may seem kind of strange to you, but let's also remember that vectors themselves are kind of strange as well. Vectors are simply arrows. They have some length and some direction, some magnitude and some direction. So it should seem strange when I ask you to multiply vectors together. And as it turns out, the process that we go through to actually multiply vectors together is specially designed to obtain particular results that we're going after. And two of the most common ways to multiply vectors are known as the dot product method and the cross product method. The dot product, which is indicated with an A for a vector and a B for a vector with a dot multiplication symbol in between, requires us to take the horizontal component of vector A and multiply it by the horizontal component of vector B, and add to that the vertical component of A and multiply that with the vertical component of B. And so that we're clear here, I'm saying that if we define vector A as a horizontal component of A1 and a vertical component of A2, and B is a vector with horizontal component B1, vertical component B2, then the dot product would be the product of the horizontal components and the product of the vertical components added together. So perhaps you'll recognize that since the components themselves are just numbers, if I multiplied a number times another number and then a third number times a fourth number and added those results together, I'd end up with a number by itself, which is true. The dot product of two vectors generally, or always, I should say, produces a scalar or a numerical value. And why this is helpful for us is that it's often used to calculate work. And work, of course, from the world of physics is the force exerted on an object to move at a certain distance. And to describe this calculation with a more geometric sense, we use the phrase projections. And I've got a whole other video that'll be talking about projections. So you'll hear me say that, the projection of one vector onto the other. We'll explain that in another video. Now the cross product, written as the vector A multiplying by vector B with the cross multiplication symbol, now that one does return a result that's a vector, and sometimes called the vector product instead of the cross product. What I hope you recognize here is that the result ends up having three components to it. And so what that implies is that the cross product only works for vectors that are defined in three-dimensional space. So if we had vector A to begin with, it wouldn't just be a horizontal and vertical component, but there's a component that includes depth as well. So generally on an XYZ plane, A1 still represents the X direction. So on a graph, a lot of times that's forward and backward movement. The A2 is our Y movement, which is left and right movement. And then A3 is our Z coordinate or Z component, and that's our vertical movement. So again, in this case, A and B need to have three components, and you can see how those are defined here. I'm not going to spend a whole lot of time talking about the cross product. When we encounter it, or if we encounter it in this particular class, we'll spend some more discussing it at that time. So let's switch back to the dot product for a moment, and let's see if we can compute dot products. Now in this example, the vector u and vector v are being defined using rectangular coordinates in the angular parenthesis form. But remember, these mean the same thing as 3, -2, for example, or if I had written this using ij notation, we might have 3i minus 2j. And all three of these descriptions mean the same thing. So when we're being asked to multiply u times v using the dot method, then again I need the horizontal components to multiply together, so 3 times 4. Then the vertical components to multiply together, -2 times 5, and sum the results. 12 plus -10 is 2. So the dot product of u and v in this case is equal to 2. The dot product in part B, again, vector u, vector v, horizontal components multiply together, so 2 times 5, and vertical components multiply together. Now there's no number in front of j here, so we assume that that's equal to 1. We'll multiply 1 times negative 6. 2 times 5 looks like 10 to me, and 10 minus 6 is 4, so we would say that the dot product in this case is 4. So it's really important to keep in mind that these are just numerical values. There is no direction associated with them. Dot products always produce scalars, or just numeric values. Now, computing dot products in rectangular form is quite easy. You just saw how simple it was. We just pick and choose the horizontal components and the vertical components and multiply them together. If we're not presented vectors that are in rectangular form, we could, of course, convert them, but there's also another way that we can find the dot product. So the dot product, in this case, in what we call our polar form, is defined as the magnitude of u, and notice I'm adding the extra bars here to be consistent with how we describe these in class. The magnitude of u times the magnitude of v times cosine of theta. And theta is going to be the angle measure in between the two vectors. So hopefully you can realize, knowing that the dot product must end up equaling a numerical value, that that's exactly what would happen here. The magnitude of u is the length of u, a numerical value. The magnitude of v is the length of v, another numerical value. And cosine theta, well, that's a ratio of side lengths, which is also a numerical value. If I have a number that multiplies by a number that multiplies by a number using traditional multiplication, we end up with a number. So the dot product of u and v does come out to be a number using this method as well. Now, if theta was given to us as the angle in between two vectors, that's great, but even if it isn't, that's okay too. Remember, if we're given the magnitude and direction of u, we tend to have the direction relative to the positive x-axis. Similarly, if I have the magnitude and the direction of v, the angle v is provided to us relative to the x-axis. And if I have the angle of v and the angle of u, then to compute the angle between them is easy to do by simply subtracting those two angles. So again, if the angle isn't specified in between two vectors, we can easily obtain it. Now, as an extension to the dot product theorem, it might be helpful to try to use the dot product to calculate an unknown angle measure as well. And I recognize that we said we can compute the angle measure if we know the angles of the prior to, but maybe that's not provided to us, and maybe we have rectangular components and we'd like to find the angle of the vectors in between. That's where this technique would be helpful. Well, I could divide both sides of the equation by the magnitude of u and the magnitude of v, and that'll be the dot product of u and v divided by the magnitude of u times the magnitude of v, and that'll leave us with an expression that's equal to cosine of theta. And to isolate theta, I would move the cosine component to the opposite side of the equation and use cosine inverse evaluated at this particular expression. So this modified form of the dot product theorem can be helpful for us in the future as well. So we'll just make a note of that here. In fact, I'll just slide this down. The extension states that the theta value that we're after could be computed if we know the dot product and the magnitude of each vector. So there are going to be several examples in the Math Excel assignments talking about dot products and computing them. One use of the dot product here would be to verify whether or not two vectors are perpendicular to one another. So recall that a perpendicular vector would mean that the theta value is equal to 90 degrees. So actually, before we do any math on this, let's think about this for just a second. If theta was 90, then the dot product u times v would be some magnitude of u times some magnitude of v times cosine of 90 degrees. Now, if you recall this from your unit circle, cosine is the x value at 90 degrees, Well, the x value at 90 degrees is 0. So what if cosine of 90 was 0? Then 0 times the magnitude of v times the magnitude of u would also be 0. Then it implies, or what's implied here is that our vectors will be perpendicular if their dot product equals 0. So you might have been thinking for this first problem, well, let's just use this extension formula. Find the angle measure by evaluating cosine inverse at the dot product, which we can do, of these two vectors, and then divide by the magnitude of u times the magnitude of v. And we can find the magnitude of u and v as well because we have the rectangular components. We can use the Pythagorean equation to find the magnitudes. But I don't think we have to go through that trouble. If we dot u and v, which in this case would be 3 times 2 plus 5 times negative 8, then the product, if equals 0, implies that we are dealing with perpendicular vectors. Well, 6 minus 40 clearly is not going to be equal to 0, and I really don't care what the number is. If it's not equal to 0, then we know that these two vectors are not perpendicular. In the second example over here, we can do the same thing. If we dot u and v, we would like to see an answer equaling 0 to determine if these are perpendicular or not. Well, the horizontal components multiply together, and we add that with the vertical components. And sure enough, negative 2 plus 2 is equal to 0. Therefore, the vectors are perpendicular. If we had drawn a picture, they may appear perpendicular, but we can't always trust our drawings because they could be inaccurate. So again, if you were thinking about the image and assumed that it was perpendicular, you definitely want to verify it with some sort of math. We could have done the same over here as well. I didn't quite have enough room to show both of these, however. But I think if you draw them clearly, we would see that they are not perpendicular to one another. Now, to finish out this video, we're going to talk about the application of the dot product in the world of physics, because we see questions like this in the Trig class as well. But the definition of work is a force vector multiplied by a distance vector, because work measures the amount of energy that's being used to perform a task, how much force is being applied in some sort of displacement. So the formula that you may have seen before is W equals F times D, and it is appropriate to use the dot symbol here because the force is a vector and distance is a vector. And if it helps to see it in words, here we go. But work by itself is not a vector, it's a numerical value. And it's technically a measured value, so it does have a unit associated with it. So let's take a look at this particular example. A force is given by the vector 2, 3. So if I were to draw that force vector, it would look something like this. It has a rightward component of 2 and an upward component of 3. And it moves an object from the point 1, 3 to the point 5, 9. So on an xy plane, that would be from this point, 1, 3, to this point, 5, 9. And I'll draw that with a vector as well. Now this arrow represents our distance vector, and in this particular case we have a horizontal component of 4 and a vertical component of 1, 2, 3, 4, 5, 6. 4, 6. Of course, we could have obtained that by taking the x-coordinates and subtracting them. So we had an x-coordinate of 5 and an x-coordinate of 1, and then a y-coordinate of 9 and a y-coordinate of 3. So 5 minus 1 gave us 4, 9 minus 3 gave us 6. But since the vector itself was drawn nicely on lattice points, we were able to count those positions as well. And so with our newly defined dot product, and the notion of the product of the force vector and the distance vector will provide us work, we can actually calculate the amount of work fairly easily. Work is equal to the force vector times the distance vector. And in this case, the force vector was 2, 3. And the distance vector was 4, 6. So the end result here is 2 times 4, which is 8, plus 3 times 6, which is 18, or in other words, 26. Now, as it turns out, our distance was measured in feet, and our force was measured in pounds. So our unit of measure here is going to be 26 foot-pounds of work. And there's always a question of, at least when I think about it, there's always a question of whether this unit is measured as foot-pounds or pound-foot or pound-feet. And for work, for the measurement of work, the unit is foot-pounds. This is definitely correct here. If you're talking about rotational movement, such as torque, on the other hand, then we would measure this as pound-feet. Because torque measures the amount of rotational force that occurs when you apply a 1 pound weight at the end of a 1 foot long lever. In most science classes, we measure work using force as a newton and lengths in meters, but instead of meter-newton forces, or meter-newton, I should say, units, the standard unit of measure is actually a joule for work. So in most science classes, again, you'll see joule or some sort of force and distance measurement using newtons and meters. And hopefully that'll prevent you from getting too confused with the unit for torque versus work. So that concludes this particular video. Hopefully you see the benefit in completing these examples and recognize how they can be applied in the work that you're doing currently. If you've got questions on the assignments that you're working through, please let me know. You can send me an email or a message through Schoology. Thanks for watching.